Hey, John, what's going on?
Hey, Craig. Not much. Happy Friday.
Happy Friday. I know you've had a busy week. You're just at what, the NGen conference?
Yeah, the Engine N3 Advanced Manufacturing Summit, which was really cool. There was some cool stuff there.
Excellent. Sorry, I had us coming back to me in my headphones, so I just had to find out where that was coming from. And then now that I've taken care of that, it's
No,
awesome. Let me just switch windows here and we'll jump right into it because we got some cool topics.
yeah.
But unfortunately, my show notes have disappeared with my jumping around. Hey, there they are. Welcome back to Future Tech, your weekly source for the latest in tech and innovation in business. I'm the startup coach, and as always, I'm joined by my co-host John Irwin. How
Hey,
you doing,
Craig.
John?
Good. How's things?
Good. And since we're going to cut off the beginning there, how was the NGen conference?
Yeah, Engine Conference was really cool. There was some cool tech. Most of the people who were exhibiting were graduates of the Engine program. So those that don't know, Engine used to be a supercluster. It's now converted into a non-for-profit. They have some of the stats that they gave were that for every dollar that was invested, I think it was like 4.8% of that, or 4.8, they get 4.8 times, the government gets 4.8 times that back in taxes. So very successful program. But the summit itself was really cool. They were talking about some of the future tech. They were talking about the future of EVs, which the listeners who listen know that I think it's hydrogen is the future. Um, and no, it was really great. Some great speakers, and got to talk to a lot of great people.
Fabulous. We might as well jump right into it because we've got a bunch of viewers already, watchers.
Sure.
Thanks for joining us. For wherever you're watching, if you have questions about what we're talking about or comments, just put them. Oh, we already got a comment coming in. Just put them wherever you are, and we'll review it. You guys look good. Thanks. Thanks,
Stéphane,
Ben. How
salut
are you doing,
Stéphane.
buddy?
Good to see you,
Nice to
buddy.
see you. We're jumping right into this. So,
Yeah,
stock market secrets. This is about quantum mechanics. Model discovers patterns in the stock market.
yeah, kind of cool. So it's new research. So they're applying quantum mechanics to the stock market. So again, it's research. It's still in its infancy, but the thing is traditional finance theory has its limitations in fully explaining market complexity. So what this study aims to do is take a truly innovative approach by using the tools of quantum physics to model stock returns. So they're treating price fluctuations as particles governed by external forces and diffusion. Similarities emerged with the quantum world that have shed new light on kind of these mysteries. So the most notable part of the discovery was power law distributions through solving the iconic Schrodinger equation, which revealed how herding behavior among investors can intensify macroeconomic uncertainty. So, kind of proving what people already knew was happening. That led to fatter tails and more frequent crashes. So, what they did was they validated this effect empirically, showing a clear link between business cycles and market anomalies. Surprise, surprise. But it's kind of cool that they used quantum mechanics for this. Such insights kind of thing would have some practical application. So, by understanding how macro conditions imprint themselves on prices, investors may gain an edge in risk management. The study also indicated that economic instability was a driver of volatility. So again, we kind of already knew that, but still cool that the tech that they're kind of applying here. So looking ahead, blending physics and finance hopefully will continue evolving. Future models may be able to simulate quantum phenomena like entanglement between correlated stocks. Researchers, I think, are also exploring machine learning combined with quantum mechanics for trading strategies, which is kind of cool because I was kind of looking at getting into some day trading myself. So this will be kind of interesting to see. But as computing power goes and new technologies emerge, quantum could offer a powerful toolkit for analyzing financial big data in ways classical statistics can't. So this is a really cool start, and I'm interested to see where it goes.
Yeah, I have to say, of all the things we're talking about today, this is the one I understand the least. When I'm like, all right, so
Same here.
we're using quantum theory to not really analyze stock market performance, but people's behavior, and then based on that, do stock market predictions and based on what's happening.
Well, kind of, but no, but people's behavior that drives stock prices, if that makes sense. So, um, like looking at the stock market from a pattern recognition, if that makes sense, but using quantum mechanics, so the thing is obviously I'm not a quantum expert. I don't fully understand how the quantum mechanic portion of it helped them to come to these conclusions, other than the discovery of the power of law distributions through solving Schrodinger's equation. Um, but again, based on this article, it's kind of cool, but it's like, yeah, we already knew that, thanks, kind of thing, if that makes sense.
Yeah, I feel like this is what's happening already. So we're just applying quantum computers and quantum techniques to analyze the stock market behavior and predict the future. Isn't that what all these black box algorithms are trying to do now? They just don't have quantum computers driving them.
Yeah, but if we were to just go a little bit more into depth, so the discovery of the power of law distributions through solving it relates to quantum physics and our understanding of nature at the atomic level. But I don't understand, again, how this completely like, the thing is I feel like in this article, all they did was they put the word quantum in front of things, and they kind of verified results. Now, obviously, it would be great to talk to a quantum expert about this and what this exactly means, but again, they used apparently quantum mechanics to reveal herding behavior among investors, um, and different business cycles and market anomalies. Like, uh, it's it's cool if this is a much more complex than what you and I are understanding, but at the same time, who knows? Um, it's really interesting um, around just kind of verifying or solidifying um, market behavior and people's behavior when it comes to the market.
Yeah, I'm just pulling up the study that the article that that we posted here, where we're looking at uh referenced.
Yeah,
And yeah, basically during our sample period, 4 years, recessionary periods, including the dot-com crash, global financial crisis, corona virus, pandemic, they did all this analysis. And it says it explains the role of economic uncertainty as a bridge between business cycles and investors hurting behavior. But the finds are consistent with predictions of the quantum model. I guess they made a model based on this, but all these things are 100% going backwards because that's how they tweak them, right?
yeah. So apparently, like, it's what they're doing is called quantum modeling. So they're exploring practical derivatives of quantum modeling. So, like, option pricing theory, portfolio optimization, and again, not investment, not stockbrokers, not we aren't any. So maybe there's a disconnect between this that we're not, or maybe there's a connection or something that is blaringly obvious to someone, that you and I aren't seeing.
Yeah, and it's fine. And again, I'm the quantum skeptic of the two of us.
Yeah.
I sit back and I say, okay, quantum's magic, and versus real science. And yeah, it feels a little like they just put quantum rather than algorithm or futuristic model or financial model. They put quantum model. Great.
Yeah.
Um, and they ran it through a quantum computer. The problem is, we both know that there's so much noise generated from these things, they can never really tell, or they have a hard time telling the positive outcomes from actual noise, whether that was just a mistake or whether that was an actual positive outcome.
Yeah.
So so this is interesting.
Yeah.
I'm curious as to where this is going. What do we got here? It's a great example of social intelligence. Like Hex AI is doing well from sentiment analysis. I guess these are all AIs trying to analyze the stock market based on behavior, cycles, herding mentality. This is, I think it's
There's a whole
interesting.
bunch of other ways too that they could utilize, like they could utilize this beyond stocks as well when it comes to any kind of financing or finance.
Well, yeah, of course. But let's face it, you might as well hit the mother load when everyone's saying, hey, we can use quantum computing to predict the stock market. A lot of people are going to start investing in that kind of companies' thought processes to make sure that, they're not going to be behind on this.
Absolutely. Yeah. It's going to be interesting to see, to see if they're going to be able to predict stock market crashes or other trading or portfolio fraud detection, different things like that when it comes to finance and it comes to stock market. So,
yeah, and it doesn't really say how long. I can predict the crash.
Yeah.
You can predict the crash is going to crash 5 minutes from now, or you predict the crash is going to crash 5 months from now.
Yeah. Yeah.
Because we have a lot of those predictors now when things happen. We're going into recession when we have more than 2 months of declining GDP or whatever it is.
Yeah, exactly. But it'll be interesting to see if this actually does prove to be something that's viable, where they're able to capture quantum effects in macroscopic systems, or if we do get widespread adoption of quantum devices like this, where their ability to simulate complex systems, if this does get widely adopted, it could radically transform risk modeling on Wall Street. It might already start to be, and we don't even know about it because they like to keep their cards close to their hand. So it may prove a whole new dimension of edge, if that makes sense.
Yeah, and they talked about quantum sensors being integrated into economic data collection. How would that work?
So when I was doing some research, so a quantum sensor, it's very real, and it's an active area of research and development. But there's some things to know. A quantum sensor is a device that uses quantum properties like entanglement or superposition to achieve enhanced precision compared to classical sensors. Some examples that I came up with were atomic clocks, magnetometers, accelerometers, gyroscopes, gravimeters, imaging sensors, more. And what they do is they work by exploiting quantum properties like spin, momentum, etc., of photons or atoms or ions, and certain solid state systems like defects in diamonds and things like that. So, for example, an atomic magnetometer uses the spin position of an atom in a magnetic field measured by optical probes to achieve ridiculous sensitivity to magnetic fields. It's crazy. Atomic clocks, which underpin GPS, use hyperfine transition frequency in atoms as an incredible stable oscillator, surpassing the stability of classical crystals. So there are quantum sensors that are commercially available, and several companies are developing some next-gen devices, but they're still, again, new technology in its infancy. But their development relies on advances in fields like quantum optics, atom ion trapping, quantum materials, and device fabrication at the nanoscale. And we're going back to this nanotechnology kind of stuff. So,
but I don't understand it's great that we're going to have these quantum sensors.
Yeah.
But where are they putting them? Like, what? I don't understand. like the data comes in through networks on the stock exchange, and they're analyzing multiple patterns,
Yeah.
like Stefan is saying here. Behavioral analysis problem. Where are these sensors actually going? Are they going on the network? Or like, I don't
Yeah.
understand.
Some of them are. So, for example, there could be traffic monitoring. So you could use a quantum gravimetric sensors could count vehicle or foot traffic in real time to better understand consumption trends and model supply chains. For financial transactions, so quantum or crypto communication protecting financial networks and quantum enabled POS systems could generate consumer spending indicators. Satellite integration, which we kind of just talked about with the GPS, but next gen quantum geomagnetic satellites performing distributed sensing globally could amass essentially kind of like a 5D economic geospatial data for big picture analysis. And just I did research on this. This isn't coming off the top of my head. And then there's automation. So quantum controls could integrate into manufacturing or logistics. So we could have real-time metrics on output, downtime, efficiency, things like that. The idea essentially is to leverage continued improvements in quantum sensing to economically extract more. It all comes down to more and more and more data.
Okay, I get it now, but and as Stefan says here, you sound like Mr. Spock. It's great if you have sensors everywhere, yeah, and you can track this stuff. Like, I wasn't thinking beyond okay, we have the stock market as exists today where we put these sensors, but you're talking about literally putting them everywhere, in roads, in trucks, in warehouses, in outhouses, in whatever. And when you see changes in any of these patterns, that now all of a sudden you can predict stuff.
Yeah, like there was a cool episode of oh my god, what was it called? It was about startups. Silicon Valley, where the guy of the VC was like he was eating Burger King, and he was noticing the sesame seeds or poppy seeds or something on the burgers. And so he's like, okay, so cicadas, something about them every so many years in one country and every so many years in another country, and both are combining, which is happening in the US actually this year. As far as two different types of cicadas are emerging, but those two events merging into one really affected the price of sesame seeds. I think it was sesame seeds. And so he invested all of his money into sesame seed futures and made a crap load of money. That's where I'm seeing this.
Yeah, absolutely. I mean, once everyone has that information, I was looking up for that scene, but I think we'd get flagged if I put it up there. Where, they're talking to this guy and he looks completely out to lunch, and like he's not even paying attention to them. And he's never been to a fast food restaurant, and he's got all this fast food stuff on his desk, and he's like never seen it. Yeah. And when he comes to this and just ignoring everybody, they're asking for money, and then he just says, yeah, he'll do it, and comes to this conclusion because he just, based on this Burger King food in front of him, he understands the cicada is going to come, sesame seeds are going to go up, he's going to invest in this, and he's going to make enough money that would more than cover any losses the company in front of him just did. So let's invest. So it was a very interesting process. It really had nothing.
That's the type of stuff. The more sensors, the more data we have, the better we can predict things, and the less who knows?
We were talking about putting these sensors on farm animals and cows and whatnot. Yeah, if you start putting them all the way through the food chain, never mind everything where else, you can do a lot more. But I also, when you start talking about quantum sensors, it sounds expensive and it sounds far away.
Yeah, it does. Certainly. Yeah.
Any other final comments on this one?
No, just the biggest thing here too is as we grow this quantum field, right? There's a serious lack of skill shortage with people with expertise in both quantum computing and financial domains, specifically with this. So, for those of you, any TKS kids out there, developing these rare hybrid skill sets would give you such an advantage. But again, only if you're interested in both of those domains.
So jump into this next one.
Yeah.
Liquid metal printing.
the T1000? No, T2000? What is it from Terminator 2? But no, this isn't that. So it's an exciting new development in 3D printing technology. So again, coming out of MIT, surprise, surprise, Massachusetts in Boston there, they could revolutionize how we manufacture with metals. So what they've done is they've created a process of liquid metal printing, which uses molten aluminum deposited layer by layer into a bed of glass beads. One of the biggest breakthroughs is the incredible speed. They can print parts like chair frames and table legs in just minutes, which is over 10 times faster than traditional metal 3D printing solutions. So some key things you might find interesting is, first, their use of a constant molten aluminum bath versus remelting approaches eliminates issues like cracking and warping. Second, the glass bead substrate acts as a makeshift mold that the aluminum solidifies into nearly instantly once deposited. So something to think about. I don't know if you have a video of it, but something that people will be amazed.
That's what we're seeing right now.
What's that?
I think that's what we're seeing right now.
Is some people that will be amazed in how it works, because they melt the aluminum, hold it in a reservoir, then push it through a nozzle, much like an inkjet printer, to rapidly build up the design, which is cool. So the one thing to note, though, currently the resolution is lower than some methods, but if you're using it in construction, you don't really, there are a lot of elements that don't require fine details. So you also, I think the researchers also showed how combining it with traditional high-res printing could actually make fully fledged products. So there's tons of future applications, from architecture and industrial design to recycling scrap metal. They even have a goal that they come up with a machine that everyday people can use, which would be scary. People using molten aluminum and glass beans. So really, really cool stuff.
Yeah, this is pretty cool. I'm trying to see if I can get a better.
Seeing a video of it is much cooler than me describing it.
Yeah, and that's why I've got the video here. I was trying to get it a bigger screen, but I'm not really sure if I can. No, it's not really going the right way for me. All right. Anyway, it's really cool to look at, but if you looked at the chair and stuff that we were seeing, it's pretty rough, like you're saying. Would you call it low resolution?
Low resolution, yeah.
So you can see it pulling out of this. It's pretty interesting when it draws and then it just deposits it. It's really cool when it looks what it's doing here. And I'm very excited. What do you think they'll be able to do with this next?
Well, there's tons of applications. Are we talking about additive manufacturing, or are we talking specifically this? Let's talk about additive manufacturing first. Yeah. Okay. So like additive manufacturing, there's tons of material science stuff. So multifunctional materials, so combining multiple materials into complex graded compositions with customized properties. So you could use multi-jet fusion printing. So properties like conductivity, stiffness can vary within objects. There's biomaterials, so 3D printing of tissues, scaffolds, implants using bio inks, cells, and biomaterials. So this, we're getting away from metal, but it's really cool to see. So this is what's called additive manufacturing, right? So there's different things. We were talking about nanotechnology, so nanocomposites, so dispersing nanoparticles into polymer matrices using techniques like fused granulation to produce materials with enhanced properties. If we get into stuff that's more closely related to this, ceramics and glass, so new techniques will allow intricate heat-resistant designs with difficult to form materials. And then going back to alloys, so direct metal laser sintering and binder jetting can precisely engineer material microstructures for optimized strength to weight kind of alloys. You could have self-healing materials. There's so many doors that are opening to advanced materials through both compositional and structural complexities, if that makes sense.
Yeah, you mentioned low resolution. How does this compare to like 3D printing now?
So there's a whole bunch of different types of 3D printing technologies. So in terms of resolution, this is what's called liquid metal printing. So there's SLA, which I can't remember what it stands for. They can achieve resolutions on the scale of 50 microns or better. So LMP trades this off and currently only able to print structures with features over 1 millimeter due to the limitations of the molten metal deposition process. So again, we're in its infancy. Again, it's a new technology, so really cool. So FFF, which is fused filament fabrication, and that's like you can have a basic desktop printer like that. They have resolutions around 100 to 400 microns, but high-end FFF can reach 150 microns. Again, LMP operates at a larger, less detailed scale than that. There's the binder jetting, which I was talking about. Whenever I say the word binder, I always think of Futurama, but metals.
Bender.
Yeah, binder. Metals, binder jetting reaches resolutions from 200 to 500 microns, depending on the material. Again, LMP prints are much coarser. So every single liquid metal printing technique, it's higher resolution than this, but this is much faster. So again, you're trading off resolution for speed, but when it comes to construction, you don't need that high resolution. And if you can come up with a bit bigger, faster speed, well, you can probably maybe build a building faster, things like that.
Yeah, you definitely do some interesting stuff with this, depending on the tensile strength.
Yes.
Are they talking about how strong the product is when?
I think I read somewhere where like the tensile strength. I don't know specifically
Because it's
what
aluminum right now,
is,
right?
but yeah, it's aluminum. So it's once it cures and cools, like it should. It's
I just don't know if I'm building any structures out of
so you can sit
aluminum.
on that. I just don't know how heavy of a person can sit on it right now. But
yeah, I just saying, like when you talk about building houses and stuff or whatnot, I'm just not sure how much aluminum goes into those structures.
No,
but the concept is cool. You could if you could pour beams or basements or whatever easy with a technology like this, easier than it is now. It definitely doesn't have to be super smooth because that's just the rough stuff.
Yeah. Could you print an I-beam, an aluminum I-beam like this much faster and start producing at mass for anything, or using it in cars? Is it that strong to withstand? So I'm sure it will get there. I just don't know if it's there yet. Like there's still a lot of challenges and limitations that are that need to be overcome to get this to kind of a commercialization kind of stage.
Yeah, it's really cool concept, but what point does it become like? Look, 3D printing has taken forever to really become mainstream, and it's still not mainstream.
Yeah.
It's too expensive. It doesn't quite do. It takes too long. There's 1,000 different things why it's not.
Yeah.
Now we look at something like this, which looks more complex, which looks more dangerous, takes more power right now.
Yeah.
How long till we get to see this kind of stuff in the hands of regular makers?
I don't think anytime soon, but I think we'll see it in maybe metal fab shops. I know that 3D printing is being used in jet engines. I think GE is using 3D printing technology. So although it's not mainstream as far as people in their houses, and there still are a lot of people. There's one company that's really doing some cool stuff. They're called Mosaic Manufacturing. They're a Canadian-based company. They're doing some really cool scaling projects. They've got a lot of cool scaling technology, a lot of cool 3D printing technology. They've got like, you could start printing garments using PLA, or I can't remember the exact material that you use, but there were some cool demos that they had them at the N3 Summit, and they are doing some really, really cool stuff.
Just trying to see if people can see how rough that is. It looks pretty rough.
Yeah, it's really
And
rough.
yeah, so I'm sure it's
Maybe
just
a
a
polish
process
might
thing.
help.
Yeah, they could probably process such a thing that you'd throw something like that on a lathe or something that smooths it down and get you
Yeah.
a nice polished surface. So I'm less worried about that, but I just wanted people to, if I don't know if they can see it, but
No.
it looks pretty rough.
The video is
The
low resolution itself.
Yeah. So, but it is interesting. I like the concept of being able to do this, because when we start projecting out from a future tech point of view, like, there's a lot of William Gibson books where the concept of the 3D printer in the local 7-Eleven, where you order something and they just print it up there, and it's more than just what we consider a printer. In fact, at one point, a virtual person uses one of these things to become real,
Yeah.
which is the conclusion of a 3 series. But when do we start seeing this kind of stuff? Like, this is great. The 3D printing revolution is great, and we're starting to see it come to fruition. Because this is more driven towards manufacturing, potentially at a higher level than, say, the 3D printing. Are we going to see this develop faster?
Potentially. And we might not even see it develop, if that makes sense, because like we see a lot of like, unless you're following this closely, they're not going to. A lot of companies are going to keep this close to their again, their cards close to their chest, because they don't want other companies to know of the advantages they have, right? So they're going to want to, or potentially they'll broadcast it. Who knows? But there's with everything going on in the world, there's less focus on things like this. But I'm sure we'll hear about it if there's another breakthrough as far as resolution, or as far as something that is what people would consider newsworthy. But I think it's going to move forward quite quickly, because there's a lot of the quicker you can print things, especially when it comes to construction. The quicker you can print things, the quicker you can implement them, and the faster you can move forward. Not like these big construction projects move too fast anyway nowadays, but who knows?
And we probably should keep in mind that this is, like I said, 3D printing randomly. So if you wanted to talk about actually building a high-res mold and just injecting the metal into it, you could get some good results. So if you were doing a repeatable thing, it's rough, because it looks like they just kind of draw a pattern in whatever, and it just sits there and all stuff sticks to it. You got to brush it off afterwards.
Yeah.
Yeah, definitely cool. I want to be able to 3D print metal stuff and robots from home.
Yeah.
I think.
Yeah, but again, the other thing too to think about is, like, they used aluminum, but what about other metals? So other metals will have different thermochemical properties, but maybe they'll work better. Maybe there's more advantages to another type of metal other than aluminum to use. So the thing is right now, I think the current prototype machine, it's only able to print parts of a certain maximum size, and that limits application. So they're going to have to scale that technology. But there's a lot of different things to look into, and even the deposition control. So precisely dispensing molten metal layer by layer over a large area is going to be very difficult to do as they scale up. So there's a lot of improvements, and a lot of different techniques, and a lot of experimentation that's going to be needed.
Yeah, I agree. And I think this is a little way out, but not as far out as some of the other stuff we've been talking about.
No.
So So let's move on to the next thing here, which is nanoscale power plants with graphene ribbons turning heat into power. What's
Yeah, so
happening here?
this is one that again is quite difficult to grasp the concept of. So this article that we're talking about, it focuses on the work of a guy named, I think it's Mikhail Perrin. He's a quantum physicist who's researching in Zurich. So he's developed a so-called nanoscale power plant that can convert waste heat into electricity using graphene nanoribbons. So what he's doing is he's combining principles of thermodynamics and quantum mechanics. By doing this, he's able to harness quantum effects for energy production with near zero loss, which is kind of cool. So graphene's unique properties is what's allowing to do this. But their unique properties allow the quantum effects to persist at even higher temperatures, like negative 23 degrees Celsius, overcoming limitations of other materials. The devices directly generate electricity from temperature differentials via the ribbons, differing conductivity when heated. So initial prototypes have demonstrated electricity generation from modest heat sources. And obviously, scaling up could tap residual heat from sources like electronics, machinery, and buildings, even people, maybe, I don't know, for power. So it's advancing. Again, I know we are always talking future tech. We're always talking the bleeding edge kind of stuff. He's developed a groundbreaking way to scavenge, we'll call it, usable energy from wasted heat. But we'll have to see where this technology goes, if it's proven further, if it can scale up. There's a whole bunch of things that are coming into play.
Yeah, I have to be honest. When I first read this, first thing in the morning, I was thinking waste heat. I'm like, is this a Mad Max Beyond Thunderdome type situation when you're talking about waste? And I'm like, oh, I get it. So anything like waste heat from electronics in laptops and whatnot.
Yeah, it's really interesting. So it talks about like capturing that heat and then converting it into electricity, kind of like how a lot of different power generation do it now, but they're using, not differentiating heat, but they're using heat, and we could also, but they waste a lot of heat. So this could be a more efficient way.
Yeah, absolutely. Laptops heat up. There's all sorts of, and if somehow we can actually capture that energy while reducing the heat, we just slap these on top of our CPUs and, we're
Yeah.
gaining a lot of extra power, I would assume.
Exactly. We could scavenge the residual heat from processors, batteries, to prolong the operation or reduce the amount of time we have to charge it, or reduce charging time, or reduce in between charges, things like that.
I'd also assume, and maybe incorrectly, that the very process of doing this is a cooling process.
I don't know. That would be interesting. So maybe um, the way that graphene nanoribbons convert waste heat into electricity is it takes advantage of varying electrical conductivity when exposed to a temperature gradient. So when a temperature difference is created across the nanoribbon, the hot side exhibits higher electrical conductivity than the cold side. So the conductivity mismatch enables the ribbons to directly generate an electric current just from the movement of the charges diffusing from the hot to the cold region. So yeah, potentially it could help to cool depending on how those charge carriers move.
Yeah, when I was looking around, I saw some notes around. Although it's not a traditional cooling system, it helps reduce overall heat dissipation by utilizing some of the heat to produced by the device for electricity generation.
Yeah.
And I'm like, okay, like you're taking the heat away and doing something with it. So that is a heat reduction. It's just a question of
Yeah, the thing is that excess heat is what's turned into electricity. So,
I agreed.
yeah,
It's like what a heat pump does. Like it takes
exactly.
when you start looking at the concepts here, and so I'm curious as to one, how expensive these things are going to be, and let's start with the obvious question: when are we going to see this kind of stuff integrated into common technology?
Honestly, so graphene nanoribbons, well, graphene technology is further along than people might know, but this kind of technology, it depends on how quickly it can be scaled. It's There's still a lot of limitations that need to be overcome in order to do this. So there's the size and miniaturization, there's the temperature range, there's material properties. So I'd say we're maybe 5-10 years off, not too far off. You know what? Now that I say that, I keep saying 5-10 years off, and we're gonna have to fact check me in 10 years if on these things to see what where we're at. Again, I'm not an expert in any of these fields. I'm just reading these articles and we're discussing them, right? So we're just two geeks geeking out.
Absolutely. So I guess the problem is, before we had these graphene ribbons, we really couldn't do this at these types of at room temperature and whatnot.
No, yeah, we couldn't. And again, most techniques of creating energy are not very efficient. So this is apparently extremely efficient, and there's no loss of heat from this. So it'll be interesting to dive into more of the details of this.
Yeah, and although it looks like they've done tests at 250 Kelvin or negative 23 degrees Celsius, it's not very warm yet. They're saying
No,
the system is expected to work at room temperature in the future.
exactly. That's where they need to get first. They need to get it working at room temperature. But again, this could, if they don't get it working at room temperature, potentially this could be a great application for maybe the Antarctic or the Arctic if they're still frozen in 5 to 10 years.
I guess, but I'm just thinking we could use it. It depends how much electricity this stuff generates.
Yeah, exactly.
Because here in Canada, this sounds great, because let's just put a bunch of these on the outside of the house and loop them through the inside of the house, and the temperature difference should create a lot of electricity.
Yeah. Well, hopefully. But
Like
and
put
we're
them
going to digress here for a
as an
second.
example, right?
But but there is actually a technology now coming out where, and it's commercially viable, I think, where there's solar panels that produce the same, if not more, than the solar panel windows that produce the same, if not more, than solar panels on your roof. And so they're integrating that into houses now. So you have that, at least for now, until we get this technology.
I think we should be doing both, right? Because
Yeah,
if far as I'm concerned, there's no reason why we can't capture the rays of the sun and do a temperature differential,
exactly.
because both in summer and winter there'll be significant differential, but usually between the inside and the outside of the house.
Yeah, yeah. Just the thing, I was just doing a little bit more research into this as we're talking about it. So the research is even at an earlier stage than we thought. Perrin was estimating it'll take at least 15 more years before the technology could be potentially incorporated into consumer devices.
Yeah, it's right here.
Oh,
Sorry, under the ribbon.
yeah,
Where
there you go. Yeah.
highlighted couple. So yeah, I guess it'll be a while. Like, all this stuff sounds great. Are we going to have our quantum batteries and our nuclear batteries and all this stuff by that point? And
I feel much more secure with a quantum battery than a nuclear battery, for sure, at least right now.
and I honestly have to going to be the person to say this, but I don't really understand graphene, because graphene apparently is the miracle thing, and it mentions a miracle material. It can be used for everything, and it solves all the world's problems, but not yet.
Yeah. Yeah. So graphene it's like a single atom thick layer of carbon atoms. and it's arranged in a hexagonal lattice. And so the basic structure element is like graphite, charcoal, carbon nanotubes, but it looks like a flat sheet of carbon atoms, if that makes sense. So it's incredibly strong, yet it's lightweight. A single sheet of graphene is 200 times stronger than steel, but much, much thinner, about 1/1,000,000th the thickness of a human hair. The other thing about graphene, it's highly conductive. It's a wonderful conductor of electricity and heat. Its electrons behave as if they have zero effective mass. And their graphene sheets are kind of semi-transparent, so only a few layers are needed to be visible to the naked eye. So there's a lot of applications with this. Like they're used in touchscreen panels, flexible displays, water purification systems, composites, biosensors, energy storage, conductive inks. Like there's tons of applications that they're being used in currently.
I just feel like to put this in common nomenclature, graphene is like using the F word. It can mean anything in any conversation. You know, you could say that is effed, or that was effing great, or that was that, you know, depending on your tone, it could mean bad, it could mean great, it could mean this, it could mean that. You can use graphene for anything, is what it feels like. It's you can use it for, you know, you rub it on your skin and it's going to take away stretch marks, and it's going to regrow your hair, and it's going to.
So so for those that are listening, so you can visualize it like a sheet of chicken wire that's made out of carbon atoms arranged in a hexagon kind of structure. So it's thin, it's remarkably durable. Again, I get where you're coming from because this is a newer technology. I can't remember when it was discovered. It was first isolated as an individual sheet in 2004. So it's, again, very new technology, something, and again, it's small, so it's hard to show, it's hard to see, outside of showing it in a diagram or design. You know what I mean?
Yeah, again, I just feel like, for lack, in the Marvel universe, graphene is what do they have in Wakanda? All the vibranium.
Yeah,
It's the thing that does all the things.
yeah. It could potentially, yeah,
It's a wonder thing. That's all I'm
yeah,
saying. That it
yeah,
can do so many things, and I'm curious to see what we actually, um, how many of these breakthroughs actually come from it.
yeah, for sure.
So, what do you have coming on, John?
Yeah, so really cool stuff. So obviously I'm going to be on February 29th, and you can talk about this. I'll be attending the Startup Drinks TO. But coming up on February 21st, I'm taking part with some phenomenal people. It's a roundtable discussion on HR, branding, and funding. That's taking place on King Street at the Creator Club. That's going to be interesting. On the 25th, I am I'm taking part as a judge for the Canadian National Leadership Conference in Toronto. It's for high school students, which is really cool. So that's going to be interesting. And then on the 29th, obviously, Startup Drinks TO.
Yeah, Startup Drinks TO is going to be great. We've got a bunch of other things coming up. Definitely, that's on February 29th. It's a leap day this year, so I think it might be our first one ever on a leap day.
Cool.
So come on out and join us. That's always good. We have, let me get rid of this. We've got mentoringmagic.ca. It's probably too late for this for most people catching this later, not watching this live. Find your co-founder at co-founder matchup on February 14th. We have, what are we talking about funding next week? I didn't look ahead.
I didn't look ahead. What do we have next week? Let me have a quick look. We are talking about Shred.
Shred. There you go. And is it Tuesday or Wednesday? Do you remember?
It is on Tuesday the 13th.
Perfect.
At 12 o'clock.
And if you want to get a hold of John, check him out on LinkedIn.
Yeah.
do we have a Startup Drinks TO arm sign? Signal? I don't know. Two arm signal. A Startup Drinks TO two arm signal. I like how he used the TO in the thing there. Thanks, Stefan. Yeah, as you know, hopefully we'll see
we haven't
you
seen
there.
you at a Startup Drink, Stefan, in a while. You have to come out.
Yeah, he's created a couple of videos on how much he loves it, but we haven't seen him out in a while.
No.
So definitely get your tickets for that. If you want to work with me, go to startupcoach.ca, book a 15-minute discovery call. We can talk about, how I might be able to work with you and how that could help. Everything else is at torontostarts.com.
Yeah.
And thanks for watching, everybody. Thanks for joining us, Stefan, and everyone else who's live watching us live on LinkedIn and YouTube.
For sure. And shout out to Ken Salta for getting me my ticket to the N3 Summit. So thank you for that, Alex.
Yeah, thanks, Alex. If it wasn't up north out of the way, I would have went. I know I'm a train guy. If it's not on the train line, I'm not going.
Yeah. Awesome.
All right. Thanks, everyone. We'll see you soon.
Thanks, everyone. Thanks, Stefan.